Electromyography is the recording of electrical activity associated with muscle tissue. The problem with many commercial devices that do this is that they're bulky, expensive, and you have to stay tethered to the lab equipment. I'm developing a low-cost Bluetooth alternative to this equipment. I have built and tested a 7-channel EMG device that has the potential to be a step in future development of advanced prosthetic control and other devices. Currently, the state-of-the-art system costs around $65,000, and the goal of this project is to get one costing under about $75. On the left, you see the Ripple front end, which is responsible for taking in the EMG data from electrodes and doing some basic filtering of that data, and it costs about $2,000. On the right, the new systems version, which is a custom circuit board designed to also take in EMG data from electrodes, it costs about $50. Next, we have our methods of data transmission. The Ripple system uses a cable to transmit the EMG data to its portable computer system, and that cable costs about $800. Now, the low-cost system uses a Bluetooth connection to transmit the EMG data to its portable computer, and adding this functionality only costs $10. Lastly, the portable computer takes the EMG data, does a little more processing to it, and then sends it on to another device, like a prosthetic hand. The state-of-the-art system is too big to fit in your pocket and must be worn on some kind of belt. That computer costs $60,000. The low-cost system's computer will be the user's own smartphone, and as the user already has this equipment, it doesn't add any additional cost to our system. My goal isn't to replace the Ripple system with my own. They have very different capabilities. For example, the Ripple system can be daisy-chained to read up to 512 channels at 30,000 times a second. My system will read 8 channels at 1,000 times a second. The low-cost system needs significantly less resources and can do significantly less, which is why there is such a price discrepancy. The EMG data comes into the custom circuit board, and it's a bit noisy and hard to read, shown in this figure. The ADS-1298 chip does some filtering, and we get much cleaner data, shown in this figure. The Teensy takes in 1,000 samples per second per channel, and then does some additional filtering and sends it over to the Bluetooth module. Using Bluetooth 2.0, we send all the EMG data to a smartphone for additional computation. Let's spend a little more time talking about the custom circuit board. A lot of considerations were made while designing this board. There was an emphasis on minimizing the space it took up, but also having a clear layout that could be easily understood by future developers. The raw EMG data comes in from the top via the electrodes. It then passes through a hardware filter and then onto the ADS-1298 itself. This data is then passed out the bottom side of the chip to the microcontroller. Here's a visual representation of what happens during filtering. After the EMG data goes through the first hardware filter, it still has some noise. A 9th reference electrode is placed to detect environmental noise. The noise signal is then inverted by the ADS-1298 and sent back to the user via a 10th electrode, and the noise signal is canceled out. At this point, the data is at the microcontroller. The microcontroller applies 2 Butterworth filters and an absolute value. These filters generate what we call features, which we send to a portable computer which identifies groups of features as movements. The intended location of this device is on a sleeve worn on your forearm. Being small and lightweight is really important here. On the left, you can see all the components of the system drawn to scale against a Galaxy S10 smartphone. The total area is about 5.5 square inches, and the weight is about 1/8 of a pound. Because usability and portability are important as well, some preliminary testing shows we can expect 6 to 8 hours of use before needing to change or recharge the batteries. One of the main goals that prompted the design of this device was to allow for more intuitive control of prosthetic devices. Other more foreseeable applications include gesture control for games or gesture control for smart home devices. So far, I've been able to get the system to sample 8 channels at 1,000 samples per second, send all that data to the Bluetooth module, and get the cost down to around $80. Future work includes receiving all 8 channels of EMG data on a smartphone, sewing the components onto a sleeve, and making the system plug and play for anyone else wanting to use it. Lastly, I just wanted to thank you for listening and to thank the University of Utah's UROP program, DARPA, and the NSF for help funding this project.